This is the fourth in a series of quarterly reports that feature progress being made by NASA's Exploration Launch Projects Office. The Systems Integration Laboratory, or SIL, is the primary facility for the initial integration of the avionics and flight software systems for the ARES-1 launch vehicle. Located in Building 4493 at Marshall Space Flight Center, the lab gives project engineers their first look at a real-time simulation of the ARES-1 ascent trajectory. The lab configuration and control system, named Maestro, can switch out avionics packages in order to gather a wide variety of data on the vehicle during flight. Marshall engineers monitor the simulated flight, examining different physical properties of the vehicle during its ascent. Data on pressure, altitude, Mach number, and velocity are gathered to help the vehicle designers optimize the configuration of the vehicle's electronics and software systems. At Ames Research Center, another computer simulation has been developed to examine abort scenarios for the ARES-1. Researchers recently completed an examination of possible debris impact with the Orion in the event of an ARES-1 mishap or explosion. The results of this study will help vehicle designers in risk assessment and safety system design. The Ames team also examined blast wave overpressure in the event of an ARES-1 upper stage explosion to determine what effects the blast wave would have on the Orion capsule. A ground wind loads checkout model was successfully tested at Langley Research Center's Transonic Dynamics Tunnel in late March and early April. These tests address possible failures on the launch pad due to ground winds, which could cause bending and shearing of the vehicle. This test successfully established Langley's capabilities for ground wind load testing. Lessons learned will be documented and applied to tests currently planned on the ARES-1-X test configuration and ARES-1 flight configuration, currently scheduled for April 2008 and July 2009, respectively. The ARES-1 5-segment reusable solid rocket booster first stage will be utilizing a newly reformulated internal motor insulation thanks to ongoing efforts at Kirkhill Elastomers. Kirkhill Elastomers, based in Brea, California, is a partner with ATK Launch Systems. They have been developing and manufacturing the motor internal insulation of the Space Shuttle's solid rocket booster for 25 years. Kirkhill is in the process of testing a new insulation for the 4-segment solid rocket motor, and that insulation will be used on ARES-1 when full-scale production of 5-segment motors begins. The insulation separates the propellant from the steel casing. A new material, PBI fiber, used in protective gear for firefighters, is being utilized as part of Kirkhill's new insulation material. It is first brought together with the other materials for the insulation in a mixing process. The mixture is then rolled into sheets and cured on racks. Once cured, the process is repeated, and the sheets are then rolled one last time through a series of rollers in a process known as calendaring until the desired thickness is achieved. Some of these sheets are then hand-rolled and extruded into the desired shape for use as seals. Kirkhill began reformulating its solid rocket motor insulation 3 years ago in an effort to prevent it from becoming obsolete. The new insulation is 10% lighter than the current insulation, safe for people to handle without personal protective equipment, and can withstand temperatures of up to 5,000 degrees Fahrenheit for more than 2 minutes. Engineers working on the ARES-1 J2X upper stage and ARES-5 RS-68 core stage engines recently completed a series of tests on subscale injector hardware. This test series focused on modifications to the injector tips to improve performance. The series also sought to determine the optimal number of injector elements per square inch to provide the best balance of performance versus manufacturability and cost. Between February and April of 2007, Marshall engineers conducted 14 hot fire tests on 28, 40, and 58 element injectors. These injectors channel liquid hydrogen and liquid oxygen into the engine's main combustion chamber. Firings of roughly 7 to 20 seconds generated between 15,000 and 20,000 pounds of thrust over a range of chamber operating temperatures and pressures. These tests found that higher element density led to better performance. For the J2X engine, which is focusing on injectors of between 40 and 58 elements, this verifies their projected performance expectations, as well as verifying the stability of the J2X at these element densities. Heat flux data obtained from the test firings will also aid in the design of the engine's main combustion chamber. In another nod to the legacy of launch vehicles inherited by ARES, work is underway at Marshall's Building 4755 to prepare for the arrival of a friction stir welding tool from MTS Systems of Eden Prairie, Minnesota. This facility was previously used in assembly of the Saturn 1C, and the friction stir welding process itself is utilized on the Space Shuttle external tank. A robotic weld tool very similar to the new system being installed at Marshall was in use on Space Shuttle tank hardware, but was damaged by Hurricane Katrina. Excavation and installation of reinforcing material has been completed, and rods that will be used in mounting the tool have been placed. A representative from MTS has also inspected the facility's work to ensure smooth installation of the tool upon its arrival. The friction stir welding process will be used to assemble different components of the upper stage in the same manner as has been developed under the external tank program for the Space Shuttle. The robotic welding tool will be shipped to Marshall and assembled on site, as the finish machine is too complex and too massive to transport fully assembled. The friction stir welding process uses a very rapidly spinning pin to fuse two pieces of metal together. This creates a bond significantly stronger and less prone to breakage than traditional welding, with fewer defects in the finished product, even under microscopic examination. The upper stage office has also recently begun confidence panel testing for the upper stage instrument unit. These panels will test the manufacturing and rolling ability of aluminum lithium panels with different rib thicknesses as part of weight reduction efforts on the upper stage. First, sheets of aluminum lithium are hand examined via ultrasound to check for internal defects in the raw material. Once the material has been hand inspected, the surface is skimmed to ensure it is as flat as possible, and a cutting tool then cuts a grid pattern into the material. The thickness of the resultant ribs is then verified by hand. For the confidence panels, a variety of different rib thicknesses are examined to determine the ideal thickness of the final instrument unit panels. After the panels are cut, a fluorescent penetrant liquid is painted over the entire surface. This liquid will seep into any cracks or other defects in the finished panel and can then be drawn out by application of a second developer chemical. The panel is then inspected under black light to illuminate any spots on the panel where the penetrant has found its way into cracks or porosity defects. In April, engineers at White Sands Test Facility conducted tests of the Peacekeeper missile's axial engine for potential use as a roll control system on the ARES 1-X test flight. This engine produces approximately 2,500 pounds of thrust. Subsequent tests at the end of April provided ARES 1-X with valuable data on the Peacekeeper engine. Analysis of the data is underway now to determine the suitability of this engine for use as a roll control solution on the test flight. For more information about ARES plans and progress, visit us on the web at nasa.gov/ARES.